Carboxylic acids are an important class of compounds. In this video, what we're going to talk about is how do we name these things very briefly, their properties, mostly their acidity, how can we affect that, and then how do we make carboxylic acids, and then what can we do with carboxylic acids, what kinds of reactions do they undergo. So naming these things is relatively straightforward. Instead of an alkane, like instead of butane, we drop the E and we add an oic acid. So a 4-carbon carboxylic acid is called butanoic acid, or we can have propanoic acid, or pentanoic acid, octanoic acid, etc. So just know that carboxylic acids are named as alkanoic acids. You drop the E and you add an oic acid to name carboxylic acids, and the carboxylic acid always gets the highest priority. So even if it's not named as an alcohol, it's named as a carboxylic acid. This would be 5-hydroxy-4,4-dimethyl pentanoic acid, with this carbon always being carbon 1 if you have substituents on there. Physical properties of carboxylic acids, one thing that's really important to mention is they generally have really high boiling points. If you notice, like the only difference between acetic acid, which is the common name of ethanoic acid, acetic acid, and ethanol, they differ by 40 degrees in their boiling point, but the only difference is the presence of this one oxygen, and the reason is because the oxygen of one carboxylic acid can hydrogen bond to the OH of another carboxylic acid, so they tend to form these hydrogen bond dimers, which then increases the boiling point. So generally speaking, a carboxylic acid is going to have a much higher boiling point than the same alcohol with the same number of carbons. Okay, and we know that carboxylic acids are acidic, and the reason that they're acidic, remember, is because if we remove this hydrogen with a base like sodium hydroxide, we get a resonance stabilized negative charge, right? So remember that this thing has a resonance structure where the negative charge is shared between both oxygens. And this thing that we form is going to be called a carboxylate salt. So for example, if we take benzoic acid and deprotonate it, what we get is a salt that we call sodium benzoate. Right, so like I just mentioned, carboxylic acids are stabilized, or the carboxylates, the anions of carboxylic acids, the conjugate base of a carboxylic acid is stabilized by resonance, and that's the reason why carboxylic acids are so much more acidic than the corresponding alcohols. How else can we affect acidity? Remember that induction can also be used to affect acidity, so the more electronegative atoms that we place close to the carboxylic acid, the more that we can decrease the pK. So notice that we get more acidic as we add more chlorines. Trichloroacetic acid is much more acidic than the corresponding acetic acid. Okay. First, what we're going to do is talk about how we make carboxylic acids. Most of these reactions we're already familiar with. Remember that you can take an alcohol and using Jones oxidation of a primary alcohol, so if you have a primary alcohol, we can oxidize it to an aldehyde, which then will immediately continue to become oxidized till we get a carboxylic acid. Now, if we want to make carboxylic acids, this is one strategy for doing that. We take a primary alcohol. Under Jones oxidation conditions, we can oxidize it to the corresponding carboxylic acid. We're also aware of another reaction that we've talked about previously. If you hydrolyze a nitrile, you can get a carboxylic acid. For example, let's say we had a 3-carbon nitrile, 1, 2, 3, in the presence of dilute acid and heat. Then what we do is we hydrolyze the nitrile to put a carbon-oxygen double bond here, so we get propanoic acid in this case. Remember to keep track of your carbons here. We have 3 carbons here, and this carbon is the one that becomes the carbon of our carboxylic acid. Also, remember how you can make nitriles. If you start with an alkyl halide like this one, then what you can do is an SN2 reaction, but keep in mind here we have 7 carbons. We have the 6 carbons of our aromatic ring plus this carbon. If we carry out an SN2 reaction, we add an additional carbon, right? Because we added this red carbon from the nitrile. So notice that the net result is that we can take an alkyl halide and convert it to a carboxylic acid, but in the process we've added a carbon. So make sure when you're making carboxylic acids you keep track of the number of carbons that you have. Similarly, let's say that we want to make a carboxylic acid from this alkyl halide by formation of a Grignard reagent. Remember, you can treat this with magnesium to get a Grignard reagent, which we can then add to carbon dioxide, right? Grignard reagents react with carbon dioxide the same way that they react with any carbon-oxygen double bond. We're going to attack the carbon, which is a really good electrophile, and break that carbon-oxygen double bond. Notice that nothing happened to this carbon-oxygen bond, so we had 1, 2, 3 carbons. We still have 1, 2, 3 carbons. But now carbon 1 is bonded to this carbon. Right, so we still have this carbon-oxygen double bond intact, but we have an O- here, and that's why we add acid in step 2, because we want to protonate that oxygen. So formation of that final OH bond gives us our carboxylic acid. Again, notice that we've added a carbon. So we had the 1 carbon from carbon dioxide that's now incorporated into our carboxylic acid. We started with a 3 carbon alkyl halide, and we got a 4 carbon carboxylic acid out. So I can't emphasize this enough. This is the number one mistake that students make, right? If we start with a 6 carbon alkyl halide here, we can turn that into a 6 carbon Grignard reagent, but this carbon right here, the carbon of carbon dioxide, is our 7th carbon. So notice that now we have 1, 2, 3, 4, 5, 6, 7 carbons in our product, and we started with 6 to begin with. So make sure you're keeping track of your carbons here. Again, like I mentioned previously, we have 7 carbons in here, but we add an 8th carbon when we do the SN2 reaction. So we start with 7 carbons in our alkyl halide. In this case, the SN2 reaction introduces the 8th carbon, which then gives us an 8 carbon carboxylic acid. There's only one reaction of carboxylic acids that we're going to worry about in this video, and that's reduction. You need a really strong reducing agent to reduce carboxylic acids. You need lithium aluminum hydride. You cannot use sodium borohydride, it's too weak, but lithium aluminum hydride will replace this carbon-oxygen double bond with 2 carbon-hydrogen bonds. And the way this works is that initially what happens, remember lithium aluminum hydride, you have this aluminum hydride reagent, which is a source of partially negatively charged hydrogen atoms, which can react with this acidic hydrogen to form AlH3 and a carboxylate ion plus hydrogen gas, which bubbles out of the reaction. Now, this aluminum hydrogen bond can attack the carbon at the same time that we form an oxygen aluminum bond, and then kicking out this leaving group leaves us with an aldehyde, which can continue to get reduced by lithium aluminum hydride using a mechanism that we're already familiar with to eventually give us our primary alcohol. So we know that we can oxidize primary alcohols to carboxylic acids using Jones reagent with lithium, with a very strong reducing agent like lithium aluminum hydride. We can reduce carboxylic acids back to primary alcohols. So to summarize, what do we need to know about carboxylic acids? We need to know that they're named as alkanoic acids. Ethanoic acid, pentanoic acid, butanoic acid, propanoic acid, butanoic acid, pentanoic acid, etc. Strong acids, carboxylic acids are pretty strong acids for those things that contain an OH group. We know that they're acidic because of resonance, and there's 3 ways that we know to make carboxylic acids. One is oxidation with Jones reagent, one is hydrolysis of a nitrile, the mechanism of which we'll talk about later on, and addition of a Grignard reagent to carbon dioxide followed by protonation. We can also reduce carboxylic acids to primary alcohols with lithium aluminum hydride.